So once we are done with training the variational autoencoder with a set of training images, we can simply remove the encoder during the testing time or the inference time and just sample Z from the prior distribution PZ, which we defined as a normal distribution earlier. Once we have randomly sampled Z from this prior distribution, we'll pass it through the decoder, which we have trained it during the variational autoencoder training phase. What this means is that from here, I will sample Z from a normal distribution with 0 and I, and then I will pass it through this, which is a function which is equivalent to a function which we have seen earlier, that we are modeling this as a normal distribution conditional upon F, Z, theta, and the I and sigma square over here. So here, the outputs here would be directly mapping to a generated image that is directly sampled from the latent random variable that we have sampled from the normal distribution. So we have also mentioned that during the VAE training phase, what this means is that the Z here, because of the reconstruction loss, we are going to ensure that all the Z here, the function that we learn in the decoder, is going to map Z into a feasible space of X, the output space of X, which means that it's maximizing this particular log likelihood over here. Here's some common architecture for the variational autoencoder. We can either use the multi-layer perceptron. This means that all these inputs and output space and the hidden layers will be simply all the neurons that are connected by different weights over here. And this would be suitable for inputs that are vectorized in this particular form. And otherwise, we can also make use of the convolutional neural networks to form the variational autoencoder architecture. So we can see that the autoencoder architecture is always an encoder. So this is actually our Q of Z conditional upon X, and a decoder architecture, which is our P of X conditioned upon Z. And we will see that it's always taking in a high dimensional input over here, which is X, and then it's gradually decreasing. So we can see that the size of the outputs of each hidden layer in the encoder is gradually decreasing until we reach a much smaller space of Z, our latent code over here, which is that's why there's a term. This is the term of encoder, because we're encoding the higher dimensional input into a lower dimensional representation of Z over here. And then once we are done with this, we'll pass Z into the decoder, and we can see that the decoder here is actually a mirror image of the encoder. It will take in a smaller input space and gradually enlarge this until the final output, which is the same dimension as the input. So here, this is the reconstructed image of X tilde. And if you still recall, earlier we were talking about that there should be a reconstruction loss of X tilde minus X over here, which actually maximizes the likelihood of the output space. And it's the same architecture, or it's the same concept behind the convolutional neural network, where this guy here is our encoder and this guy here is our decoder. So we can see that it takes in a higher dimensional space and outputs a Z that is of a lower dimensional space, and in the decoding phase it resumes the lower dimensional space into the same space as the input space. Here's a visualization of the learned manifold for the generative model with a two-dimensional latent space. So what this means is that we input an image, and then in this step here, Z here is simply in a two-dimensional space before we pass it through the decoder. So this is our X and this is our X tilde, and this is our encoder, this is our decoder over here, and this guy here is in the two-dimensional space. We can see that as we vary the two-dimensional space, so according to Z1 and Z2 here, we can see all the samples that we sample from Z and output it from the decoder. There is a disentanglement in the latent factor. What this means is that we can see that in this particular Z1 dimension over here, the person's head pose changes from looking towards the right side to looking towards the left side, and somewhere in the center over here he's looking straight ahead. And we can see that this means that this particular dimension of the latent vector is controlling the head pose over here in this particular example over here. And we can see that this attribute here is disentangled from the second dimension, which is Z2 over here. So it's gradually changes from a frowning face to a smiling face over here. So this is a frowning and smiling. So this means that Z2 is controlling this particular expression of the guy's facial feature. And we can also see from here that in this case here, there's also a gradual change in the two different dimension of Z1 and as well as Z2 over here. You can play around with this untangled feature by this particular program over here, which can be accessed over this link. You can where you can actually change the latent random variable of the decoder. This means that I have a decoder which is going to take in the latent random variable and output an image of a digit. This particular Z here is 12 dimensional. So you change this, that means that you are changing the vector of Z to input to this decoder, and you will see how it changes the output of the digits over here. So just now I mentioned that the variational autoencoder, it's an unsupervised learning technique. So VAE here, unsupervised learning technique. This means that all the training data that we have is simply just the images that we are given. There's no need for any labels to this or outputs to this particular set of images. So what if we have the labels? This means that for every image, considering the MNIST data set, for every image that I have a corresponding class or label of that digit, or maybe for a image of a room, I have the corresponding room type. So I have this x1 all the way to xn, and I have a large sample of this as a training data. We can change or modify the variational autoencoder into what we call the conditional variational autoencoder here by simply replacing x conditional upon z, which is our decoder here, with a condition. That means that we are conditioning it upon the y over here, which is the label that we have for the inputs of x. And similarly, we should also replace the encoder where it's originally q of z conditional upon x with q of z conditional upon x and y, where y here is also the label that we have. So this label here will correspond to the particular latent code or final latent space that we want. And finally, we'll go through the same KL divergence procedure to get the same lower bound and minimizing the reconstruction loss as well as the KL divergence loss for the latent space. Here's the diagram to show the conditional VAE. So this part of the VAE is exactly the same. So everything here, this part here is all the same as before, except for now, instead of just inputting x, we're going to also input the label, the known label, into the encoder as well as the decoder. So normally the implementation would be that I have an input vector, or I have just the image where I can vectorize it into a vector, the two-dimensional image, I vectorize it into a vector, and I will concatenate the y, this label here at the end of this vector. So this is x over here, and I will simply concatenate y at the end of this particular vector over here. And it's the same for the input to the decoder. I would have z over here. Originally, I will vectorize this. This already comes with in the form of a vector. I will simply concatenate y over here and input it into the decoder. And everything else in the conditional variational autoencoder would remains the same as before. We'll just simply treat this as a new inputs to our decoder as well as our encoder over here. And during the test time, it will also be the same. We'll remove the encoder and simply sample z from the normal distribution. This is our latent code that we wish to sample, and then we will concatenate the desired y over here. We condition upon y over here. So this simply means that I'm going to concatenate these two vectors together, z and y, and input it into my decoder, and that will generate the image. That is, now what's interesting here is that because I know a certain label, say for example in the previous original variational and autoencoder. Let's say I want to generate an MNIST data where I want to generate an image which contains certain digits, but I have no control over that digit because here I'm sampling basically from the whole latent space. So I don't know what am I going to sample here. I cannot control the digit, but as long as I can condition it upon a label, this means that I can say that y equals to 0, and I'm going to condition it upon this and randomly sample z from the normal distribution. What this means is that this output here would be 0, but depending on the sample that I drew from the normal distribution, the style and the handwriting of this 0 might be written in a different form, but it will always be 0. So similarly, if I condition this upon 1, then what this means is that by sampling z here, my output will always be 1 over here, and it would be a different form of 1, for example, a different style of writing 1, for example. So here's an example of the conditional variational autoencoder where we conditioned upon the image visual attributes. Here's the attributes that we condition upon instead of just randomly draw a random sample that can contain all the different attributes here. I also want to control this attribute by inputting a vector, like for example, a young girl with brown hair is smiling. So this is what I want to condition upon, such that the outputs here would be different samples of the young girl with brown hair that is who is actually smiling, and this would be my condition, my C over here, and the variations on this from these images would be determined by the random sample that I draw from the normal distribution. Now let's move on to look at another form of network, which is called the mixture density network, and this mixture density network is highly related to the concepts of mixture model that we have learned in the previous lecture, in lecture 7. So here's the problem setting for this mixture density network. For input and x and an output t, the goal of supervised learning is to learn a model conditional distribution of t of condition upon x. What this means is that I'm learning a deep network here which takes in input of x and it's going to predict some output of t. And the usual way that we model this is that we will model this conditional probability t condition upon x in a discriminative way. So this is our posterior distribution. So we want to, that means that we want to learn a function here that takes in x and over a certain parameter, the learning parameter. We want to make use of this deep network as a universal approximator to approximate this or to learn this particular posterior distribution directly. Hence, this is actually a discriminative model that we are talking about here in this usual way that we are doing it. And now the usual way is that for each input there can only be one output, which is t over here. And we'll use the unimodal Gaussian distribution to model this particular posterior distribution for many simple regression problems. But unfortunately, this actually leads to very poor prediction for some inverse problems with multimodal distribution. So here's an example of the forward versus the inverse problem, and why inverse problem is so difficult. Consider the kinematics of a robot arm. So the forward kinematic problem is to find the end effector. This is the end effector. This is the robotic arm with just two joints over here. So this is joint number 1 and this is joint number 2. Hence, we can control, assuming that this is a planar robot, a planar manipulator arm, we can only manipulate the angle, the in-plane angle, the in-plane rotation angle theta 1 and theta 2 over here. And our objective here is that given theta 1 and theta 2, we want to find the end effector location x1 and x2. So this is easy to compute given that we know the arm's length, or L1 and L2 over here, by simple geometry. So this is the forward problem, the forward kinematic problem, where there is no ambiguity. Given the theta 1 and theta 2, you'll always find the solution a unique solution to x1 and x2. However, this would not hold true for the inverse kinematic problem or the inverse problem in this example here. So suppose that I give you, now I invert the problem around, where I give you x1 and x2, the n-vector location, and I ask you to compute theta 1 and theta 2 over here, given that I know L2 and L1, the manipulator arm's length. The problem here is that unique solution might not exist, as shown in this example here. There are actually two possible configurations subjected to the constraint of L1 and L2 over here, that we can reach the n-effector location of x1 and x2 over here. So this would be theta 2 in one configuration and theta 1 in one configuration, and this would be theta 1 in one configuration and theta 2 in the other, in this particular configuration here. So in this case, we say that this is an inverse problem and multiple solutions might exist in this case here. So it's not trivial to solve this problem. And if we were to assume a unimodal Gaussian distribution for the output space, for this output space of theta conditioned upon the input space of x over here, then this is not going to be a unimodal distribution, because multiple solutions can exist here. Here's another example to visualize the multimodality problem, or the inverse problem. Suppose that we are given this function, a sinusoidal function, where t is our output and n is our input over here. This is a sinusoidal function plus a certain uniform distribution. So we'll generate the sinusoidal function here is represented by the red curve over here, and the noise uniformly sampled from a uniform distribution will end up of giving us t from the green circles over here. So these are all perturbed with some form of noise, and the forward problem is to train the network with a learnable set of parameters f here, as denoted by this particular network over here, to find t, the red curve over here. So in other words, we are trying to model discriminatively this model over here, t condition upon x, and we are going to use a deep network of fx over here, that such that it maps to all the output of t, and this is the curve. The red curve is the one that we are going to learn, although from noisy data of all the green circles over here. And we can see that the solution is unique. That means that given every x over here, there's only one solution that corresponds to t at every x over here. But now let's consider the inverse problem, where we simply switch the role of x and t. That means that we flip these two axis around. So this used to be the x-axis, now it becomes the t-axis. This used to be the t-axis, now it becomes the x-axis. We can see that the problem now is that for some of the x, we might have multiple solutions for t over here. And by modeling this distribution, the posterior distribution of t conditional upon x over here, as a unimodal Gaussian distribution, this means that I'm modeling this particular function that takes in x and outputs t over here as a normal distribution. This means that I'm modeling this as a unimodal Gaussian distribution will not make any sense anymore. This is because now I have multiple solutions, and hence the correct way to do this would be to model this as our Gaussian mixture model. So we need to model this such that instead of a unimodal distribution, we model it with a mixture of Gaussian distribution, such that for any input of x, there could possibly be multiple. The model can actually generate multiple outputs here to model this particular green curve, or the observations of the green circles here. So formally, here's how we model the mixture density model. We'll simply model the inverse problem of multiple solutions using a mixture model that we have seen in the previous lecture, in lecture 7 in particular. So now the posterior distribution here, instead of given by simply a normal distribution that is parameterized by the network of x or t condition upon f over here, and with a certain sigma square, we're going to model this posterior distribution with a Gaussian mixture model, where pi here is our mixing coefficient, mu here is our usual mean, and sigma here is our usual variance of a certain kth component of our Gaussian mixture model. And what's interesting here is that we'll design the deep network. We'll design to learn this, a deep network to learn this Gaussian mixture model by simply outputting the parameters of this Gaussian mixture model. This means that I'm going to design a network such that it takes in x over here, and this particular network is going to give me the mixing coefficient for all the Gaussian components 1 to k by taking in x as my input, as well as it's also going to give me all my mu's from 1 to k, and taking in x as my input, as well as sigma square 1 to k, where it's taking x as my input as well. So once I have x and design this particular deep neural network where I take in x, I'm going to output all the parameters for the Gaussian mixture model. Thus, I would have a posterior distribution in the form of a Gaussian mixture model here. And this somewhat also turns the discriminative model into a generative model, because what this means is that we are also able to draw samples from this distribution here, or from this posterior distribution here. Now here's an example of a two-layer mixture density network with a sigmoid or tangent hidden layers as the activation function. And what this means is that I'm going to take in all the inputs of x1 to xd. So these are my d-dimensional inputs, and the outputs would simply be denoted by a k pi, where this is simply corresponding to the coefficient of pi, which is our mixing coefficient, as well as I'm going to output sigma k or a k sigma over here, where this corresponds to the kernel width. And I would also have a L dimensional output, k by L dimensional outputs of the means. This means that for every component, or for every Gaussian component, I have a L dimensional mean that determines the component of mu, which is the kernel center of my Gaussian mixture model. So the total dimensions of the output would be L plus 2 by k. K is the number of components, L is the dimension of my means, and 1 for the mixing coefficient, as well as 1 for the sigma. So here, sigma, the covariance, we're also assuming that it's isotropic. So you can have a L dimension, L by L covariance matrix, but we'll use sigma square for the diagonal here to simplify the whole estimation parameters. Here, as usual, the mixing coefficient must satisfy the following constraint, where it must sum out to 1, as well as it must be between 0 and 1, such that it can satisfy the categorical distribution. And this can be achieved in the neural networks as a softmax output. So if I put A here, which I mentioned that this A pi is the output corresponding to my mixing coefficient, I'll simply add a last layer. So this is my network where I output A of pi over here. I'll simply put it into the softmax over here, such that this will enforce a constraint to make it into the mixing coefficient that fulfills these two constraints over here. Now, we'll do the same for the variance, that there's also a constraint that the sigma square must be always more than and equals to 0. And this can be implemented as an exponential, differentiable exponential function in the last layer of my neural network. So I have a neural network F over here, and the input is going to output A of sigma over here, which I'm then going to put it into the exponential function, such that I can ensure that this sigma square here is always more than or equals to 0, because exponential function is always more than or equals to 0 here. Finally, because the means have real components, they can be directly represented as the output of the network, where there is no constraint needed for this particular mean of the Gaussian mixture model. Now we can write the loss function of the mixture density network as a negative log likelihood. So recall that this guy over here, this particular guy over here is our Gaussian mixture model, which corresponds to our this likelihood function of t condition upon x, or the posterior distribution. So now we can simply take the negative log likelihood and use it as a loss function. As I've mentioned earlier, that the loss function simply means that we need to minimize this guy over here. We need to min this loss function over all the weights, where W here simply represent the learnable weights in my deep neural network that will output all the parameters of the mixture density network. So similar to the EM algorithm, we will end up with a responsibility equivalent function over here, which is dependent on all the parameters of the all the estimation from the previous parameter of the network, and we will simply define this as gamma over here, which is equivalent to our responsibility function. The next thing that we can do here is that we will after the forward propagation where we get gamma, we can then keep it fixed over here or pre-computed over here, and we will simply partial differentiate all the loss function with respect to all the learnable parameters or the output parameters that we want, and back propagate it to the all the way through the network. And these are the gradient terms that we will get for the respective component. So once we are done with the mixture density network, we can simply use this deep network as to estimate this particular posterior distribution here, where T is our target data and X is our input data. So we can simply take, given a certain input, we can simply output the T over here, where now since this is a multimodal distribution, so for a single input of X, I can have a different output for T over here that corresponds to a different probability of my mixing coefficient. And now the last thing that we need from the inference of the mixture density network is to determine which one of the solution from the mixture density network would be the most probable. So since I mentioned that each one is a Gaussian mixture model with k components over here, this means that we'll get k number of outputs for each particular input over here that corresponds to all the means, or the mu1 to mu k here simply refers to every one of this is one plausible solution for the output of T. And one simple way is to simply take the mean, the expectation over all the solutions. This simply means that we are going to integrate over dt over here, the expectation of this the output space over here. And then we can also simply calculate the variance using this way, the expectation over the T minus the expected value of T square. And this can be easily done by simply replacing P here with all our Gaussian mixture model, where pi, the mixing coefficient, and mu here are simply the output from the deep network, taking in X, as well as we can make use of pi, sigma, and mu that is output from the deep network to estimate this S square over here, the variance of the estimation. So what this means here is that despite that we have multiple solutions for T, we are simply averaging all the solution to get the final solution for a single input of X. But there is a problem with this. This means that the solution might not be physically feasible. So in this example here, if we were to take the average of this theta 1 and theta 2, so this is one set of solution, as well as theta prime 1 and theta prime 2. So the expectation or the mean over these two solutions would be simply theta 1 plus theta 1 prime divided by 2, and theta 2 prime plus theta 2 divided by 2. So these are not feasible solutions. The actual solutions are either one set of this particular solution over here. Taking the average simply might end up with a pose or a pose of the robot that is infeasible given the constraint of L1 and L2 here. So in these cases, the conditional modes might be of more value, but and what this means is that we are going to take, given the outputs of pi, k, x, sigma square x, and mu x over here for that parameterize my mixture density network. I'm going to take all the conditional modes. This means that I'm going to take the peaks of this mixture density model as my solution. But unfortunately, the conditional mode for the Gaussian mixture model requires numerical iterations, and it is not always corresponding to only the mu's or the means of the particular network. Here's an example where it's actually a two-component Gaussian distribution with two means over here, but by putting it together, we can see that there's actually a third mode that actually occurs over here. And in this case here, to find all these modes over here is not trivial. We would have to do MCMC sampling from this target distribution here, or we simply do a form of the numerical iteration starting from any point here, and we'll get to the maximum by using gradient ascent algorithm. So this is computationally expensive. And hence, a simple alternative is just to take the mean of the most probable component. What this means is that I will simply take the mu k of x that corresponds to the largest pi k, which is the mixing coefficient that is output from my deep neural network. Here's the example of the simple toy problem to visualize multimodality that we have seen earlier. A plot of the mixing coefficient pi k over here as a function of x can be seen in this particular plot over here. So each one of these curve over here simply represents pi 1 x, pi 2 of x, and pi 3 of x, where we have a three-component Gaussian mixture Gaussian distribution. And we can see that for both the small and large values of x, there is a very high probability of a certain component respectively, because over here we can see from the data distribution that indeed there's only one unique solution for both small and high values of the input of x over here. Whereas in contrast, the mid-range of x over here, the mixing coefficients are more equal in the probability. This is because we have different multiple solutions over here, as seen in this plot over here. And what we can do here is that in order to determine the solution, we can simply take that component. For example, here, if x is equals to this value over here, we can simply take the second component, the output from the second component, which corresponds to the largest mixing coefficient, and as the output of the t that we want to use. Here's another plot of the mu, the means, over all the different three components across different values of x over here. And we can see that this has the same color coding as the mixing coefficient that we saw from the previous slide. Here's a plot of the final mixture model over all the different x over here. So this is my posterior, the output of the mixture model, which is simply given by sigma of k, sum over k of pi k x, and my normal distribution, which consists of t conditioned upon mu, which is a function of x, and sigma square, which is also a function of x over here. And plotting this out, we can see that this is a nice distribution that models the data input, where if we were to take the conditional modes of this guy over here, or the peaks over here, we can see that the red dots over here, it nicely models this data distribution here as compared to a unimodal Gaussian distribution.